Folks, here's a fairly lengthy video in which I explore the circulation form of Green's theorem. In the first two objectives, I'm just going to cover background information, so jump forward to whatever point in the video you're interested in viewing, or feel free to watch it in its entirety. So the first thing I'm going to do is I'm going to cover the definition of the 2D curl. Then we'll explore visual interpretation of that curl. We'll give the circulation form of Green's theorem, and then we'll work an example. Let's give the 2D definition of the curl. So given a vector field f and its coordinate functions, little f and g, we define the 2D curl as, so let's say the curl of f as partial g partial x minus partial f partial y. Now, as we often do at this point in the course, I've just given the description of the curl in some sort of shorthand notation. Let me elaborate that. The curl is really a pointwise definition, and so for a vector field like f of xy is equal to f of xy comma g of xy, the curl of f at the point x comma y is given by partial g partial x evaluated at the point xy minus partial f partial y evaluated at the point x comma y. We could be more concise with our notation here and still not lose anything if we write g sub x of xy minus f sub y of xy. But what I want to stress here is that the 2D curl is a number at a given point. So once I give an x coordinate and a y coordinate, I can calculate the number that is the 2D curl. So generally, when you see the curl described, you will see this shorthand notation, but sometimes it's helpful to look at it in the longer description to remind yourself that it's a pointwise definition. So now let's see if we can visualize the curl at a point inside of a vector field. Before doing so, I want to warn you that the technique isn't usually practical. I've carefully selected the example to illustrate the 2D curl that I want to use, but most of the time this illustrative technique is not going to work. To warn you against this right at the beginning, here are two similar vector fields. And here I've labeled the point P1 and the point P2 on each. And it turns out that the curl at point 1 is 0, while the curl at point 2 is negative. So the curl of F1 at P1 is 0, and the curl of F2 at P2 is negative. Without doing the calculation for the curl, remember that calculation was the partial of g with respect to x minus the partial of f with respect to y. Without doing that calculation, I can't discern between these two situations, and I don't think that you can either. So to reiterate, you can't always just look at a point in a vector field and identify the curl. Usually you have to do the calculation. So that said, let's look at the vector field f of xy is equal to y cubed minus 4y, comma, x cubed minus 4x. I've plotted that here. So what I'd like to do is to examine the curl of this vector field at a few points. In a moment, we'll zoom in close to this point right here, which I'll label as P1. Then we'll zoom in on this point right here, which I'll label as P2. And then we'll zoom in on this point right here, which we'll label P3, and we'll also examine the curl around a few of these points. So let's zoom in on that point P1 and see if we can determine the 2D curl at that point by inspection. That is, we're not going to do the computation at first. Before we do that, let me say though that as I zoomed in on this point, I went ahead and increased the number of vectors in the vector field, and I scaled down their lengths to make it a little easier to look at. But you'll see, for instance, over here in the lower left-hand corner, or excuse me, the lower right-hand corner, it's quite messy. And that happens a lot when you're working with these vector fields. That's part of the reason why this intuitive method that I'm trying to show you won't be very practical for more complicated vector fields. Nonetheless, let's get back to trying to compute the curl at P1. So as a reminder, what was the curl? Well, the curl was found by taking the partial derivative of the y component function with respect to the variable x minus the partial derivative of the x component function with respect to the variable y. Again, that was for some vector field that had the component functions f and g. So what I'd like to do now is, before we dive into our specific point, let's just remind ourselves of how we got those components of the vector. So let me just look at this point right here, where we've sketched a vector corresponding to that point from the vector field. And just as a reminder, when I talk about the x component of that vector, I'm talking about this vector right here, or this magnitude anyway, right here, that we get by evaluating the function f at the point, as opposed to the y component function, which we get by evaluating g at that point. So I wanted to remind you of that because we're now going to look in depth at this curl calculation. So focusing just on partial g, partial x, let's see what's going on at point P1. As a reminder, before we talk about the g, when you take a partial derivative with respect to x, the way we think about that is we fix the y coordinate and then we run over a swath of x coordinates. So I'll go ahead and sketch that. We're going to be looking at sort of this strip of x coordinates here, and then we'll be asking ourselves the question, how is g changing? So I'm using the dark brown for the g vectors. So the g vectors are these y lengths, which I'm sketching here, a few of them. Now, we can't actually use this information out here. That's a little bit too far away from our point P1. But closer to P1, what do we see the y coordinates of this vector are doing? This has a sort of a longer negative component, and here we have less and less and less and less. And so what we see is as we move from what? As we move from left to right, the y components of the vectors are increasing. Let's write that down. So as we move from left to right, the y components of the vectors in the vector field near point P1 are increasing. That's the information we glean from this statement right here, and so we would say that the partial of g with respect to x is greater than 0. So now let's do the same computation, or similar computation, for our partial f, partial y. So remember, when we take a partial derivative with respect to y, we're going to fix an x coordinate. So we're going to fix the x coordinate of P1, and then we're going to ask ourselves the question, how is whatever entity we're looking at changing as we move in a y strip from bottom to top, remember. So let's go ahead and sketch what? Well, we're looking at where partial f, so we're asking, that's the x component of the vector over here. So we're saying, how is the x component of the vector changing as our y values move from bottom to top? So notice over here, we've got a positive x coordinate. There it's 0. There it's slightly negative. Here it's more negative. Here it's more negative. Here it's even more negative, and further as we go up that swath. Okay. So what we see is that as we run, or as we move from bottom to top, the x components of the vectors in F near P1 are doing what? Well, let's see here. This is a small positive quantity. That's 0. That's a little negative quantity. More negative, more negative. They are decreasing. So that tells us that partial f partial y is less than 0. So when we do this curl calculation at P1, when we do the calculation partial g partial x minus partial f partial y, what do we find? Well, we said that this component right here was positive. We said that this component right here was a negative, and a positive minus a negative is certainly going to be positive. There's no ambiguity there. So we could say that the curl there is positive. Now I'm going to clean up this picture. So let's erase it. So another way to interpret the curl is to say, let's say we had sort of a pinwheel right here. And if we were to, for this fixed point, look at what's happening at this point, if we imagine the vectors as flow, this would be causing a counterclockwise flow, or counterclockwise rotation at point P1. That's what we mean when the curl is positive. Now, we just analyzed this picture very, very carefully. I want to remind you of my first warning. As a reminder, I first put up these two vector fields and said the curl at P1 is 0 and the curl at P2 is negative. Although the vector flow lines are moving in paths around this point 1, there's no real difference in how the vector flow lines would be hitting this side of the pinwheel versus this side. And so there's going to be no rotation at the pinwheel there. Whereas right here, there's enough of a difference. These pinwheel lines are slightly, let's see, I said the curl was negative. These pinwheel lines right here are slightly longer than they are right here. That's going to cause a net clockwise rotation to this pinwheel. It's going to cause it to spin in a clockwise manner. Unlike the example that we just analyzed more carefully, I don't think that you can look at these two images and tell which one is going to result in a rotation and which one's going to result in the pinwheel just being stuck there because of the evenness of these flow lines. I don't think that can be visually determined without looking at the calculation. So let's look at the second one of these points that I said we were going to look at. So here I've zoomed in on what I labeled P2. Let's do a quick check to see if we can determine what the curl is at P2. So we're going to look at the computation partial g partial x minus partial f partial y at point P2. Well, here we can quickly ascertain that as I move from left to right, what are the y components of my lines doing? Well, because those vectors are purely vertical, we can just say what are the vectors doing, and we see that the y components of those vectors are decreasing as we move from left to right. So we just showed that partial g partial x is less than 0. Remember, partial g partial x is that x swath. When we look at partial f partial y, we're going to look at that vertical swath and ask the question, as we go from bottom to top, what are the x components of these vectors doing? And again, this is very easy to ascertain at this particular point because these vectors don't have a whole lot going on with them. They're all, in this case, horizontal. I missed that slightly. So we see that partial f partial y in this case, how are the x components of the vector changing as I go from bottom to top? They're increasing. The x components are getting longer, moving more to the right as we move from bottom to top. So if we compute the curl at point P2, we have that partial g partial x minus partial f partial y. This is a negative number, and we're going to subtract from that another negative number, and so the curl is less than 0 here. So let me erase the lines for our P2. And so another way to interpret that is, as I said before, if you put a little pinwheel right here, let me offset that slightly, you put a little pinwheel right here, you could see that it would rotate in a clockwise manner, and clockwise manner rotation would correspond to a negative curl. But let's see if we can get the computation for that in this case. As a reminder, this vector field is the vector field f of xy equals y cubed minus 4y, comma, x cubed minus 4y. Oops, x cubed minus 4x. So let's go ahead and actually compute the curl of this vector field, and we're going to use this throughout. So the 2D curl, which there's lots of ways you could denote this. I don't want to confuse it with the 3D curl for later on. So let's just write 2D curl, and I'll write of f, meaning this comes from the vector field f, at the point xy, would be what? Well, we're going to take the partial derivative of g. Careful, here is our g component function, and we're going to take the partial derivative of g with respect to x. So when I do so, that gives me 3x squared, that should be red. That gives me 3x squared minus 4. That's the partial of g with respect to x, and we're going to subtract from that the partial of f, which is this component right here. We're going to take the partial derivative of f with respect to y, and so when we subtract from there, we will subtract the quantity 3y squared minus 4. But this gives us, when we simplify, 3x squared minus 3y squared. And so if we compute the 2D curl of f at the point we were just looking at, that was the point 2, 0. Oops, I apologize. This was the point 0, 2, 2. What do we find? We find that the curl at that point would be 3 times 0 squared minus 3 times 2 squared, or a negative 12. So we see, yep, the computation confirms that we have a clockwise rotation at that point there. Folks, I just want to say it one more time. In general, you can't just look at a vector field and determine whether or not at a point you have clockwise rotation, counterclockwise rotation, or no rotation. You have to have a very accurately drawn vector field, and you have to analyze it very carefully. And even then, I don't know whether you could always determine what the curl is at a point through inspection. So it is the calculation that you need to be doing if you want to figure out what the curl is at a point. So lastly, I want to look at the curl at point P3. But now we're going to use, and this was the, I didn't write this down, these are the coordinates 2, 2. But now we'll go ahead and use our computation here right off the bat. So we said in the previous, during the previous calculation, we said that the 2D curl of f at a point x, y, we computed that to be 3x squared minus 3y squared. So you can see that if we took the 2D curl at the point 2, 2, that's going to give us 3 times 2 squared minus 3 times 2 squared, which gives us 0. That is, one way to interpret that is if you had a pinwheel sitting right there, that pinwheel would not rotate at all. Let's move just slightly, so we're going to just move around in a few different locations here. So let me jump over here, and let's jump over here, and let's look at the curl at those 2 points approximately. I'm making these up. So let's say that this would be the coordinate, let's say it has the same height, so that's still a y coordinate of 2, but now the x coordinate is 1.9, 2. Well, if I go to compute the 2D curl of 1.9, 2, this would be 3 times 1.9 quantity squared minus 3 times 2 quantity squared, and in this case we get a negative value, and so that would correspond to, if you put a pinwheel right here, that pinwheel would want to rotate in a clockwise rotation. Remember that clockwise rotation corresponds to a negative curl. Instead, if we were to look at this point right here, which maybe we would think of as the point 2, 1.9, I think you see what's going to happen. So if we did the 2D curl at that point of f at, looks like I forgot my f's on these. The 2D curl of f at this point, that would be 2, 1.9, but I think we can answer the question here. Right away we see, okay, the x coordinate's larger and there's symmetry, and so we would have a positive curl, which means if you put a pinwheel right here, you would expect it to rotate in a clockwise, or excuse me, a counterclockwise manner. And you could just check, for your own sake, go ahead and check, see what's the curl at this point and what's the curl at this point, and figure out whether or not those correspond to no rotation, counterclockwise rotation, or clockwise rotation. So that concludes a quick visual interpretation of what the curl is at a given point. But as a reminder, we will usually just do this through calculation, and we won't actually look at the vector field, and we won't look at various points. I hope this is helpful. So folks, our next goal is to go ahead and state Green's theorem in circulation form. So let's go ahead and give the preamble to that theorem. So here's the run-up to Green's theorem. It says, first of all, that we're going to be dealing with a connected and simply connected region over, of R in the xy plane. So that could be some region that, I don't know, maybe looks like this. So there's our region R. And the requirements are that R be connected and that it be simply connected. And we looked at those definitions earlier. It also says suppose C is a closed, simple, piecewise smooth, and oriented curve, oriented counterclockwise. So what we have around our region R for its boundary is some curve C, where C has to be meet each of these requirements. It's closed, it's simple, it's piecewise smooth, and then most importantly, that it be oriented counterclockwise. That's probably the easiest thing to forget. So finally, what we have is that all of this can be thought of as living inside of some vector field F. So let me just sketch a few of the vectors of our vector field F. And let's put some around the boundary too, because we'll need to be able to point to them. So in blue, we've got our vector field F. So we do say that F has to have component functions where you have continuous first partial derivatives. So those are all the run-ups to the statement of Green's theorem, which says this. Green's theorem says that if you were to evaluate the circulation, and by the way, let's go ahead and give that a counterclockwise orientation to it. If you were to evaluate the circulation around the curve C, remember there's a couple ways to denote that, but we'll first just write it this simplistic way, f dot dr. That computing that circulation around the boundary is equivalent to computing the sum of the curls at each point inside the region. So that's the curl, remember we denoted as the 2D curl as partial g, partial x, minus partial f, partial y. That's your 2D curl, and we're going to sum that up over the entire area of that region. So let's just look at a visual interpretation of that. What we're saying here is that if you were to add up each of the curls at each of these little points sitting inside, maybe this is rotating clockwise, and here we've got a point that's rotating counterclockwise, and here we've got another point, it's rotating counterclockwise, but a little bit less so, or clockwise, but a little bit less so than the first. And here we have one that's, I guess these are all running clockwise. Here we have a counterclockwise. If you were to add up all of those curls at all of those points over R, that's what the right-hand side of this form of Green's theorem is saying, that's equivalent to simply adding up all of the components of the vector field F that fall within the tangent vector of our curve C. So along C, you can imagine here is a tangent vector of C, and maybe at that point we've also got some vector of F, and so we take the dot product of F's vector with the tangent vector to the curve at C. That gives us the component of F that's running in the same direction as our curve. We add up all of those little segments. That is equivalent to adding up the curl on the interior. So there's our statement of Green's theorem. So folks, I'm not going to do the proof of Green's theorem here, but I do want to give you a little bit of insight as to why this works. So let's look at our first region here, R1, with the curve C1. So if I were to look at, let's suppose that in all of these places I have little pinwheels sitting inside R1 here, and let's suppose each one of these has a positive curl to it. So all throughout the interior of this region, we have a positive curl. The sum over the entire region has a positive curl. What Green's theorem says is that we would also expect to have positive circulation. That is, if the vector fields are arranged in such a way so that all these points are spinning, have a positive rotation, then what we must have is that for the majority of the time at least, the vectors of f, the blue vectors of f along the boundary of that, along C1, should be moving basically in the same direction as C1. Likewise, let's suppose that at every single point here we have the blue vectors of our vector field are pointing in the opposite direction of our unit tangent vectors, or roughly the opposite direction. So here are our unit tangent vectors pointing in this direction. Then we know that this should have negative circulation. But additionally, what we would see is that, at least in some, you can't say this for every single point going this way, but at least in some, we would expect that the majority, maybe we've got a couple of points with a, let's say this one has a counterclockwise rotation and this one does, but the majority of the points in this region, in terms of sum, should have a clockwise rotation if the circulation along the boundary is negative. Likewise, if all of the pinwheels here are motionless, meaning they at each point we have a circulation of 0, then we imagine that in one sense the vectors that are causing it to rotate, maybe this vector right here, are being counterbalanced by maybe a vector, say right here. And so there's no rotation occurring at any one of these points. Well, that's the same thing as saying that the circulation on the boundary would be 0. So these three extreme cases should give you a little bit of insight as to why Green's theorem holds, but for the true insight, you'd have to look at the proof of it. So now we've developed an intuition for curl, and we've given the explicit statement for Green's theorem. Let's apply Green's theorem to an example. So here I've got an example where we're going to take a vector field f, which has component functions y and x, not very complicated, and then we're going to define R to be the region inside a square with the following vertices, and C to be a curve that traces the perimeter of that square counterclockwise. We'll go ahead and answer some questions about this. So I've gone ahead and actually sketched this vector field. There is no reason to sketch the vector field to do the problem. You do have to sketch the region, but I'm only sketching the vector field here for illustrative purposes. What you would be expected to do for this problem is to go ahead and sketch the region, and notice the region we said in the description of the problem had the vertices at 0, 0, had vertices at 1, 0, at 1, 1, let's approximate that maybe right about there, and another vertice at the ordered pair 0, 1. And so we can sketch out the perimeter, or the boundary is a better word for it, the boundary of this region as these four sides of the square. That's our boundary, and we're told that it needs to have a counterclockwise orientation, which is what we want whenever we're going to go ahead and state Green's theorem. Otherwise, we'd have to worry about adjusting signs slightly. To be honest, that's a real pain. So here I'm going ahead and giving our orientation arrows. By the way, this curve is not a smooth curve. Green's theorem didn't say we had to have a smooth curve, it said we had to have a piecewise smooth curve. Notice that this curve does have corners, but we're going to then have to break it up into individual sections when we compute the circulation. So let's go ahead and look at the statement of Green's theorem. The statement of Green's theorem says if we want to evaluate the circulation along this curve here, C, and remember the circulation is taking f dot dr, that is equivalent to computing the sums of all of the curls for all of the points sitting inside the region. And let me go ahead and shade the region R green right here. So for one more visualization of Green's theorem, what we're saying is rather than trying to compute the curl, remember the curl we think of as putting these little pinwheels here and asking to what degree does it want to rotate or not, at all points inside the region, we could evaluate that. Evaluating that, though, is equivalent to asking the question if for each of these vectors here, I sketch a unit tangent vector, which isn't very exciting for all of these lines, but there's a unit tangent vector, and here's a vector on our vector field here in blue. Let me address that. We will then take the dot product, which will give us some scalar component in the direction of our tangent vector. Out of colors here, let's do this orange. We'll add up, for that point right there, we'd add up that orange number. We sum that all along the curve as we trace through it in a counterclockwise manner. So for example, right here, this would have a positive circulation. Over here, though, if I take the unit tangent vector to the curve, let's see, maybe that's the unit tangent vector to the curve, and then I look at dotting that with the vector in the vector field, my orange quantity is going to be something negative that's equivalent to the length in the same direction as the tangent vector. So that's going to have a negative circulation here. And we will also see, for example, if I take a unit tangent vector down here, in this case, along this side of our curve, when we take the dot product of the black vector and the blue vector, we get 0 because those two are perpendicular to each other. So we would have 0 circulation along here. So let's go ahead and compute these two quantities separately. So the first thing I'd like to do is let's compute the circulation, and we'll check that. So the circulation we wrote as f dot dr, and I'm going to break this up into 4 separate line integral problems. That sounds like a lot. We'll see that they're not too bad to evaluate. So we'll take c1 of f dot dr plus c2 of f dot dr plus c3 of f dot dr plus c4 of f dot dr. Now, one thing to keep in mind is that this originally had a counterclockwise orientation. You never need to draw that counterclockwise arrow, but I'll just draw that to remind us. So when I go to give my parametric descriptions of C1, C2, C3, and C4, I need to make sure that as I give those parametric descriptions, I continue in that counterclockwise manner. So what I'd like you to do is go ahead and pause the video and give the parameterizations. Oh, I should label these. Let's label this one here as C1. This will be my C1 curve. This will be my C2 curve. This will be my C3 curve. This will be my C4 curve. By the way, you see why, besides the fact that having the vectors isn't really practical for doing the calculation, you can see why we don't always draw the vector field. It just gets so messy to draw this picture. In fact, I'll go ahead and move this all down so we don't have the vector field in the way. Great. So here I've simplified our picture slightly by removing the vector field. And what I'd like you to go ahead and do is give parameterizations R1 through R4 for each of these curves. So pause the video and go ahead and do so, and then we'll resume. So folks, here I've gone ahead and given all of the parameterizations to each of these curves. Of course, there are many different parameterizations for any curve. As long as your parameterization yields a line and it starts and stops at the correct points, then you've done it correctly. Let's just check my C4 to make sure I did that correctly. So for C4, notice that when t is 0, when I start the parameterization, I want it to spit out the point 0, 0. But if I plug in 0 for t, that gives me the vector 0, 0, which we go ahead and match with the point, or with the point 0, 0. Then if we plug in for R4, a 1, that's going to give us the vector 1, 0. Sure enough, that gives me the ordered pair 1, 0, which is where I wanted to stop the parameterization for C4. You can check my other parameterizations to confirm that I've got those right. If you're having trouble with parameterizing curves, you need to come see me as soon as possible, because everything we're doing in this section requires you to be able to come up with these parameterizations. So let's resume this calculation now that we've got the parameterizations, reminding you that for f, our function, our vector field function, is y comma x. And so for each one of these parameterizations, in place of the y, I'm going to put the second coordinate description for each one of these. And for the x here, I'll put the first coordinate description into each one of these. Additionally, we'll need to be calculating r prime of t for each one. And so, for example, I'll go ahead and write out for r1 of t, its derivative, r1 prime, would be the vector function 0, 1. So let's go ahead and set this up as an integral, and we'll do the computation. So the total circulation all over our closed curve C here of f dot dr, well, that's equal to, for curve 1, we're going to parameterize that from t equals 0 to 1. And we said that we will take the y component and list that first in our vector field. So that's t comma 1. So in a way, just look at r of t, and because of the way our vector field's given, and that's unique to this problem, I simply swap the coordinates there. That has nothing to do with the multiplication by r prime of t, which in this case is by the vector 0, 1 dt. By the way, folks, I should just remind you that what I'm doing here is we're saying that for the circulation over C of f dot dr, that's equivalent to the integral from a to b of f of t, so we parameterize it with respect to t, dotted with r prime of t dt. So that's the calculation that I just did below here, or that's the replacement that I just did below here. So let's set up one more, and then I'll leave you to set up the other two. So this would be plus the integral from t equals 0 to 1. Now I'm going to look at curve 2. So this is for curve 1 here. This is for curve 2. And our parameterization was 0 to 1 minus t. So that makes our vector function 1 minus t comma 0. And we're going to dot that with the derivative of that, which is the derivative of r2, which would be negative 1 comma 0 dt. So go ahead and pause the video and finish out the separate line integrals for curve 3 and curve 4 as well, and then we'll join back. So folks, I realized I made a mistake when I first replaced, for my curve 2 here, I was looking at the wrong function. This should have been, for curve 2, we've got the parameterization x is equal to 1 minus t, and y is equal to 1. And so when we give the description of the vector function, I want y, which is 1, and then I want x, which is 1 minus t. And that's how I should have written that. You can see then I've also given the parameterization, or the line integrals for C3 and C4. At this point, this does look like a big long mess, although in this case you can see that things won't be too complicated after we do the dot product. So I'm going to go ahead and do the dot products of each one of these, and then we'll evaluate these integrals. So go ahead and pause the video, do those dot products, and we'll check our work. So I went ahead and did each of those dot products. For example, for the first one, I dotted t comma 1 with 0 comma 1. So I did t times 0, which is 0, and then 1 times 1, which is 1, which is where we got the integrand of 1. So I did the rest of those. And here we can see that we can quickly evaluate each one of these. So this will just be 1 plus negative 1 plus 0 plus 0, which gives us a net circulation of 0. Really quickly, I want to go back to our initial picture here, where we predicted that curve 1 should have a positive circulation. And sure enough, that's what we found. Curve 1 had a positive circulation of 1. Curve 2, we said, should have a negative circulation, and that was based on looking at the directions of those vectors in connection with the direction our curve was heading. And sure enough, we found that curve 2 had a negative circulation. Curves 3 and 4 had zero circulation, and we saw that when we looked at the dot product of the unit tangent vector shown there in black with the vector field function shown there in blue. They're perpendicular, so their dot product is 0. That's true all along curve C3, and it was similarly true all along C4. So in this case, we got 0 circulation for this. One way to interpret that is that if you had a a boat sitting in tracks here, where maybe a boat sitting here, you could imagine it having a wind at its back, because in the direction it's heading, that's also the majority of the direction of the vector field. That would send us up in this direction, giving us a positive circulation, but that would be perfectly counterbalanced by the fact that if we had a boat sitting here with a sail, and the wind in this case would be in front of it, yielding a negative circulation, because the boat wants to be heading in the direction of the path, but the vector fields are pushing against it. The vector field vectors are pushing against it. So there we did the calculation using line integrals. And folks, I know this has been a long video, but the whole essence of this video boils down to this fact right here. We would now like to compute for this vector field the double integral over all of R of partial g partial x minus partial f partial y dA using Green's theorem. But what should we get as an answer? By Green's theorem, we should get the same answer that we got over the circulation for the boundary. So again, what we're going to do here is we're going to look at each single one of these points sitting inside the boundary here, and at each single one of those points we're going to ask the question, what is the curl at that point? We're going to sum that up over all points in the region, and we should get an answer of 0 as well. In this case, we'll get there very quickly. I don't want you to think that just because we get the answer faster with the curl formulation of the problem, that that's always going to be the case. In some cases, the circulation problem will be easier to compute. And so you should think of Green's theorem as permission to translate a circulation problem, closed loop circulation problem, that is, to a curl problem over an interval, or over a region. Or if you have a curl problem over a region, you have permission to translate that to a circulation problem over a closed loop. Regardless, remember that our vector field function was f of xy is equal to y comma x. So when I compute partial g partial x, that's going to give me the value 1. When I compute partial f partial y, that's going to give me the value 1. So if I go ahead and plug those into, or if I look at the curl calculation then, we would have that the double integral over R is equal to 1 minus 1 dA, which is equal to the double integral over R of just 0 dA. At this point, you should recognize that the answer is clearly going to be 0. But what I'd like to do is just set this up, because in more complicated problems, you'll actually have to evaluate this double integral. And in this case, I'll evaluate this double integral as the iterated integral, going from x equals 0 to x equals 1, and the integral from y equals 0 to y equals 1. Why am I doing that? Because that describes the region R here. Remember, the region R had x values that ranged between 0 and 1, and y values that also ranged between 0 and 1. Of whatever our curl calculation comes out to be, in this case 0, so there's no more work to be done. But then we'd have times dy dx for our iterated integral. And this does indeed come out to be 0, and Green's theorem says that is no coincidence that the behavior around the boundary in terms of circulation was equal to the net behavior over the entire region in terms of curl. That concludes that example, folks. Oh, I guess I should say one more thing. And notice that since partial g partial x minus partial f partial y is equal to 0, that tells us that partial g partial x is equal to partial f partial y. So that means that f, the original vector field, is conservative. Since f is conservative, another way to interpret that is f is irrotational. And if you think about what it means for this vector field to be irrotational, that means that each one of these pinwheels does not move. I'm not saying that there are no flow lines here, folks, and you saw when we gave the vector field there were flow lines, but they were sort of evenly dispersed throughout so that none of these pinwheels would spin. So the field is irrotational, and also it's a conservative vector field, which means when you computed the circulation around a closed loop, by the fundamental theorem of line integrals, you expected to get 0, which is exactly what we found. Folks, these are complicated ideas. I highly recommend that you watch this video a couple times. Do let me know what your questions are, and we'll talk more about it.